Hi, I'm Jean-Jacques Greffet. Okay. Can I go on?
Yes, of course. Go ahead.
Thanks, Rémi, for a beautiful talk. I had questions regarding the intermediate part when you were discussing absorption versus scattering. So if I understood correctly, the reason why you don't get absorption when there is scattering is that part of the light is reflected. So it escapes the material and then it's no longer absorbed. So that's correct. The energy that is not absorbed is gone in reflection.
Yes.
And this is also the reason for this upper bound that you mentioned. Is it related to some Fresnel reflection factor of some kind of average medium?
Yeah, and actually, I think we haven't done that, but I think that the difference could be explained by exactly plotting the energy Fresnel factor given the effective index that needs to be calculated.
Okay.
But that's it. That's a very simple picture. And actually, that's those two different curves. I haven't discussed too much why we have two curves and so on. But in the paper, what we did is that we also checked that by. So we've shown that once we've reached this homogenization regime, then we can explain everything with actually with the relative transfer equation. So we also have another way of seeing it. But that's typically that. I mean, it's just an effect of the effective index is not zero, is not one, sorry. So you get reflection, that's it.
Okay, so if I have a last question.
Go ahead.
So you discussed only absorption due to the particles. So the surrounding medium, I guess, was vacuum. What would happen if you were in a host medium with losses? So the particle would have no losses, pure scattering, and the host medium would have losses.
Yes.
Have you looked at that?
No, but that's of course interesting and something we would like to do. There are two. So I can suspect that you have two processes that will compete. One of them is that you have, if you start with a material that is absorbing, that is homogeneous, you add particles. So you could say, then I have scattering, so I increase absorption. So this will reduce absorption, whatever you want to do, okay? But at the same time, since you have scattering, you will increase, let's say, the light or the photon path in the medium. And this goes in the sense of increasing absorption. So my qualitative vision of this is that this is a competition between those two processes that can give you a decrease or an increase of absorption. Now, the second part of the answer, Jean-Jacques, but you know that very well, is that technically it's not easy. Because you have to understand what we mean by computing scattering by a particle inside an absorbing medium. And then you face, I mean, if we are in this picture of scatterers inside an absorbing matrix, then you worked on that long ago, but it's also a different story in terms of doing it properly. So that's something that remains to be done.
Thank you very much. And congratulations again.
Thank you.
Do we have more questions?
Hi.
Hello. Hi. Go ahead. I'm Ilko.
Ah, okay. My turn. Thank you. Thank you for the great talk, and thank you for having exactly this slide in front of us. Is it true that, let's say, if we have any uncorrelated pattern at any density, we can go from the uncorrelated phase to a hyperuniform one?
No, I mean, it depends what you mean in practice. I mean,
I'll say even in a simulation.
Yeah.
So the hyperuniformity, is it connected to the density of particles at all or not? Maybe not.
Yeah, okay. So in that case, so if you look at this slide, when
Yes.
we go from the red type of distribution to the black type of distribution, we have the same number of particles, so the density is unchanged.
Mm-hmm.
Okay, so everything I've shown is moving from disordered to hyperuniform at a given density.
And now the question is,
but now, of course, but now when you produce hyperuniformity, so we produce hyperuniformity so far here in the computer, okay? So we have an interaction potential. So if you want to look, we have borrowed an algorithm to Torquato, okay? So it's kind of fictitious potential that you put, and then you minimize the energy in your distribution. That's more or less the idea, okay? But of course, you can define a degree of correlation because you start from something that is almost completely disordered, and if you tune hyperuniformity to the maximum, at the end you get a crystal. And then how fast you go by changing the interaction potential, how fast you go from something that is completely disordered to something that is almost crystallized depends on the concentration. Okay, so I hope that answers your question, but there are two different things. Okay, but in our case, concentration is always the same. Okay.
Yes, and if you can show the graph of transparency of the hydrogel, where you found the critical.
Yes, sure.
And if you can explain us what is on the horizontal axis.
Oh,
like
just the position. We measured. So we use this OCT microscope. So you have a region of interest that is the field of view of your microscope. And so if you look at on the left part, okay, we have defined 6 positions across this medium where we did the measurement. So we just 7. So we measured the mean free path at 7 locations going through the transparency region. Okay, so it's just
okay, and then
yes.
And then the real parameter, what will that be? Did you identify the real parameter or the parameter?
So what we measure here is the scattering mean free path in micron.
Yes, when you zoom in on a different patch, but do you have, what is the physical quantity which is different from patch to patch?
Yeah, okay, very good. So what happens here is that, so what we change from left to right, so those material chemists are amazing people because in their process, they can fabricate this material that is typically 1 centimeter. Horizontally, you have a gradient in collagen concentration.
Okay, so that's what you probe there.
So the concentration in collagen changes here. So from left to right, if you want, the x-axis is a change in collagen concentration. And what we've shown by correlating those measurements to the microstructure that we measured by TEM, okay, because they cut the sample and they could measure it, is that this increase of mean free path, which means this increase of transparency, corresponds to at a given concentration, then you get this very peculiar structure, okay, where you start to see that the collagen fibrils are really organized. So it's still disordered, but you get this organization. That explains that the scattering is reduced by correlations, but at this stage, I cannot do more. I mean, it's qualitative.
So what you see there, is it a critical point? Can you check critical exponents and all of that?
Okay.
It looks like.
I mean, it looks like, but I mean, we're not at that stage. So I don't know if it's really a phase transition. Okay, I've used critical because it's a critical concentration in terms of that's where everything happens. And if you go towards lower or larger concentration, you lose transparency, you lose mechanical properties, you lose everything. Now, whether it's really a phase transition that we could characterize with, I don't know. Okay, so I'm sorry, I don't want to speculate too much because this is beyond what we did.
At least from that graph, you can derive some critical exponents. Just
yes.
Just feed the data with.
You're right. We could.
And then you can check at least universality and another sample. Would those critical exponents are the same? Then maybe a case can be made towards. a
You're
phase
right.
transition.
Yeah. Yeah.
Thanks, Emil. Do we have more questions?
Sure. May I ask one?
Yes, of course.
All right. Thank you. Yeah. Great talk. Thank you. I really enjoyed. Just wanted to kind of get some ideas about the assumption behind this. I was under impression that the suspension is, you know, a single phase, or you know, more or less a you know, homogeneous by itself, and you know, and for that, I'm wondering, you know, how many, say, terms in the S of Q, the complex tensor, is necessary, you know, for arriving at the you know, correlated, you know, say, scattering effect, and yeah, what will be the situation if it is a binary mixture, for example, of you know, two different scatterers that are correlated and with different probability? Thank you.
Okay. There are probably several questions in your question, but so if you have a binary mixture, then you can extend this concept of structure factor to a binary mixture. So then, to make it short, everything is the same. I mean, you get a formula for the scattering mean free path that is connected to this extension of the structure factor. That's actually what we measured here. I didn't want to go too much in the details, but in that case, actually, it's a binary mixture because we have large and small particles. So what you get here is the equivalent of this S of Q for the binary mixture. From that, we can compute a mean free path. Actually, we did that in the paper if you want to look how we do that. So just the technical stuff, but it's the same idea. Okay, in the talk, I have, in the conceptual part, I have focused on a monodisperse distribution to make it simple, but this can be extended to binary mixture or even more complicated distributions. I hope that answers the question.
Yes, thank you.
Okay.
Thanks. Do we have more questions from the audience? Emil?
Since we are on this slide, how can we get these porous structures made in a lab?
So what they did here is that they use this so-called nanoscribe technique, where you start with a polymer, and then you have a focus beam, ultraviolet beam, that locally induces photopolymerization. So it's a huge job to get that. Because you have to learn how to really handle this technique, but that's the way they did it.
So okay,
I told you more or less everything I know about that, because that's not that easy.
So in other words, it's outside.
But it's a challenge. So that's why I was showing this, because it's a real challenge to do that.
To do that, yeah. I was wanted to challenge Maumer to 3D print this, but I guess there is no chance.
No, we can print it.
Well, it depends on the wavelength range. I mean, because of course, if you target near-infrared or optics, the story is not the same as targeting a terahertz or even microwaves.
Yeah,
okay,
but
so that strongly depends on the wavelength range you want to target. But if you want to go to optics and you need structures that are on the order of 1 micron or below, then it's a huge stuff to fabricate.
Yeah, I was thinking even about acoustic wave, because this will look like really a good absorbing material. So
yes,
it will give us really nice these soundproof rooms. Yes. But I'm not sure what kind of algorithm we'll use to produce such.
Well, if you drop me an email, I can send you back some references where you have the algorithm to produce those structures in the computer, and then see how we can fabricate them. Yeah.
So is it true that the bone will have will be a hyperuniform structure?
I don't know. I know you have some bones that have a porous structures. Well, okay. Actually, I don't know. You have. It's funny because you have, especially around Torquato people, you have they try to hunt every signature of hyperuniformity they could find in natural systems. So so far I've never heard about bones, but maybe, I mean,
bones.
I don't know. Yeah.
Yes, I've been at a workshop organized by Torquato and close collaborators, and indeed some of the talks were about feathers in birds, and they found again hyperuniformity. So
yeah. So probably following the literature by Torquato, which is not easy because he publishes a lot, but if you want to get up to date catalogs of everything that that shows hyperuniformity, probably where you have to look at.
We have more questions.
Can I ask?
Maybe. Yeah, Ricardo. Yes, go ahead.
So this is not probably a question; it's more like a curiosity. So regarding the cornea discussion, so the cornea, is it always better for a cornea to have a lower refractive index, so just to be transparent and do nothing, or it would be? Let's say my question is, if you make an artificial cornea and we have a refractive index 2.5, because nature does not have that easily in a biopolymer, can we do a better cornea that has better features, or it's always better to be transparent, so the opposite, better the lowest refractive index and nothing else? Because your structure would be transparent even for very high index.
Yeah,
right?
So I got the question. I don't know how to answer, because of course, if you think about the purely photonic property, you need to avoid reflection. So the lower the index, the better, I think. But now, and that's part of this work with Nadine, is that there are probably many properties to optimize at the same time, because your cornea has to be biocompatible, which is obvious, but it also has to have mechanical properties.
Yeah.
That are, properties of biological tissues and so on. So if, all in all, it seems that this hydrogel is a good compromise, but it's certainly not only optimizing photonics and then looking at mechanics or the other way around. It's probably finding the best compromise. It's funny because if you look carefully at what we've measured, we are very cautious, okay? Because every time you speak with biologists, specialists of that, you can get into troubles. But I know there are controversies about how those things are actually produced in vivo. So it's absolutely not my field. So I'm very cautious. But in the paper, we have evidences that probably our hydrogel, let's call it this way, I don't know if it's exactly what happened for the cornea, has the best mechanical properties, not exactly at the maximum of transparency. And we measured pig cornea, so real corneas, but not human corneas. It's in the paper. Same is the same. So maybe, the optimization makes that you need to be transparent over, I don't know, 1 millimeter, and to get the best mechanical properties, but maybe you could be even more transparent, but then you would reduce the mechanics, but you don't need that, because you just need a mean-free path that is large enough so that over 1 millimeter you're transparent, but you don't need to be transparent over 2 millimeters. So you see, it's a bit subtle, because you optimize a lot of things. As you know, transparency, you have an exponential law, so whether you get a factor 1.5 or a factor of 2, it changes the story in practice. So, okay.
Yeah, you'll need the cornea of an eagle, so which, perhaps has more optimized to see is there a difference or not.
Maybe.
Thank you, Rémi.
Sorry, I muted myself. Any other question? maybe let me try to make one. I will try to be as clear as possible. I'm coming from a very ordered media, which means only considering crystals. So I know this kind of procedure to treat them in acoustics, mechanics, electromagnetism. Let's just take a very simple case. If I say I take your particles in a square lattice and I copy it, and then I am free. I'm basically having two crystals, and I'm free to twist them like the twisted graphene, or I'm free to, let's say, to move them in a weird angle in a way that at the end I could, of course, make a quasi-crystal, but in general, I will not. I will make something that is not periodic. So then I am ending up to some extent to something having this some uniformicity in your language. Are you? I mean, have you looked at that directions, or have you tried to connect this, let's say, order the properties of crystals and to connect them to diffusive media, like in your case?
So thank you for asking. So I did not, but do not consider me as the expert on hyperuniformity. Okay.
Okay.
But what you're saying is true. By the way, a quasi-crystal is hyperuniform. Okay.
Okay.
For the same reason as a crystal is hyperuniform. So starting from something that is hyperuniform in that sense, inducing disorder, how close you stay to something that is really hyperuniform, although disorder. I mean, this has been studied. You have people that have studied that. Again, if you drop me an email, I can send you some references. But I would, if you want to enter that, I would really recommend that you enter through this review by Torquato, 2018, that really gives a complete picture. But it's not an easy question. Huh? That's why I'm also a bit cautious. Probably you ask because you know it's not easy. It's not obvious how much hyperuniformity you keep when you, for example, you start from a crystal and you start to disorder it randomly. I mean, you can lose hyperuniformity very fast or not. So it's a topic by itself actually. To really, okay. And how much you connect by, you start from a crystal that you disorder and you start from a disordered system, you induce hyperuniformity. What happens? I mean, it's not easy. So these are hard questions actually. But you have real experts that actually study that.
Okay. And maybe a last one regarding the bounds that you have mentioned on this slide that should be like in the middle of the talk. How do you get this bounds, for example, on the maximum absorption? I think it was 2 slides before this one, or maybe.
Yeah, but I haven't said so much. Okay. So apart telling you just look at the paper. No, I mean we. Okay. It's really writing properly an energy balance.
Okay.
For the average absorbed power. So it's an exact result that we have, but it's the first part of that paper. So basically, you write. It's a mixture of writing energy conservation for a scattering problem. So you have the optical theorem that comes into play, if that rings a bell for you, and averaging.
Okay.
Okay. Because we compute the average absorbed power, and then we can get more or less, very roughly, we get that the absorbed power, the average absorbed power is P0, which is the incident power, minus the remaining scattering part of the system. Okay, you get a residual scattering that at the end of the day is at least due to the effective index, as Jean-Jacques Greffet was pointing out. But we get, it's an exact result. Okay, so so you have P0 minus something to make it simple. Okay, so you want to make this minus this something very small. And what we have shown is that by hyperuniformity, you can get this thing very small and get to the maximum value. So that's without writing equation, I think I cannot tell you more, but the ingredients are energy conservation, optical theorem, and averaging.
Thanks. Is there any more questions from the audience? Sebastian?
I've got a naive question. Rémi, you mentioned that it would be kind of tricky to homogenize such things. I mean, I cannot use the usual to-scale asymptotic methods. I mean, considering a supercell or things like that. I mean, how would you?
I mean, you don't have a small parameter or a large parameter. I mean, what I was pointing out, I'm not saying nothing can be done. I'm just saying that it's not like changing the density and assuming that the distance between particles becomes small compared to lambda or something like that.
Ouais.
We don't change the density. So, for example, the average distance between particles is just the same. So that's why it's not, you know, that's why I was meaning by saying it's not the usual, or I'm not saying it's easy, but I'm saying you have usual ways of handling homogenization. Here, it's different.
Okay. And you know, this 1966 paper you mentioned by Ashcroft and Lechner, can you just go back, because I think I totally skipped what you said. So really, why do you think that this is a seminal paper?
Because then, well, people in condensed matter physics think that it's an important paper, not only myself, because people were expecting that in a liquid metal, since you don't have the crystal and the usual bond structure and so on, then electrons would be scattered so much that the resistivity would be very large.
Okay.
And then they measured and they found that the resistivity was much lower than what the naive argument you would get by saying it's completely disordered and you have diffuse propagation of photons and you get Ohm's law of electrons, sorry. You get usual Ohm's law and the reason is that it's not completely disordered. You have a sort of factor that you see here, and then you have to compute correctly the mean free path. And when you do that, you feed the data. Okay, so in 1966,
at that time, that was
an obvious statement. Okay, but okay.
Oh, no, okay. Okay, thanks. Great talk, by the way.
Thank you.
Thanks, Sebastian. Do you have any more questions? If not, let's thank Rémi again for the nice talk.
And thank you again for inviting me.
Thanks. It was recorded and it will be available on our webpage in the next few days. And you will receive a DOE attached to it such that it can be cited.
Excellent. Thank you so much.
Thank you, Rémi, and thanks to everyone for attending. And see you next week.
Enjoy your afternoon. Bye-bye.
Thank you.
Bye.